All right, what is up, you guys? So today I'm going to be doing something a little bit different besides reading from Differential Geometry by Erwin Kreyszig, which is still, I would say, my main series going on right now, the Differential Geometry with Erwin Kreyszig reading stream series. But today I'm going to be answering a comment from a viewer like you where they bring up that they had on a midterm that they had, which by the looks of it is from undergraduate abstract algebra. So I'm just going to read exactly what their comment is, and this is from Diego Torres 2101. So shout out to you, Diego Torres. Hey man, I was wondering, you ever thought about doing quote deeper unquote videos? I really enjoy the problem solving and all that, but what about something more fun, like a problem from group theory, Galois measure theory, etc.? I'd really love to see how you go about that. I mean, to give an example from my last midterm, let H and K be normal subgroups of G, where H and K are disjoint sets. Show that G is isomorphic to some subgroup of G mod H cross G mod K. I can give a few more ideas, but to be fair, my knowledge is somewhat limited. But yeah. So this is what happened. Diego Torres commented on my video, Bergman metric and kernel, the crossover between complex analysis and differential geometry. And I woke up in the morning and I saw in YouTube Studio that there was this comment, and I can see just the top of it. I couldn't see the problem yet, but I could read already that there was a problem in the comment. And I thought to myself, all right, whatever this problem is, I have to do it and I have to make a video solving it. So then a few hours go by, it's now early afternoon, then I read the full comment. And at first glance, I'm gonna be honest with you. So I know what a group and a subgroup are, disjoint sets, all that. But if you would have turned the gun on me and you asked me, what is the definition of a normal subgroup? That would have been it. Also, same goes for isomorphic in terms of group theory, just to be honest with you. And then I was also thrown off because I'm rusty in abstract algebra, if it isn't clear to you already, but I was unsure if that / notation was modulus or if it was complement, like a set complement. And that's honestly, I don't do anything with abstract algebra in my day-to-day work besides, I guess, my little side Rubik's Cube project. But even then, the day in, day out of like making progress on that project does not involve like solving abstract algebra problems. It's just knowing the names of what's going on in like a program, which what's going on are things, you know, like cosets and all that stuff, which are like abstract algebra concepts, right? But the reason why I could tell that this is an undergrad abstract algebra problem is I feel like a midterm for graduate abstract algebra would already be far beyond normal subgroups and stuff like that. So not that there's anything wrong with it, because obviously I just told you that I read this comment early afternoon. I did not immediately sit down and start going about solving it. But what I did do is I cracked out my international paperback edition of Dummett and Foote Abstract Algebra, and I perused the sections. I mean, I obviously clarified the / notation. I perused the beginning sections of this book, you know, reminding myself the definitions of normal, subgroups, isomorphisms, so on and so forth. And then I kind of just like threw it on the back burner of my subconscious, unconscious, and just went about my day, went about my activities for a few days. And then yesterday or so, I sit down and I'm like, all right, pen and paper. I started writing down, I wrote down the problem, wrote down the definitions of the things involved, because let's be real, if you just got the problem and you were in my similar scenario where, okay, you know what's going on in abstract algebra, but you're rusty, you don't know the exact definitions off the top of your head, and you just read the two sentences over and over and over, and you just reach into the depths of your mind trying to pull up something in order to solve this problem. It's not going to happen unless you actually have those definitions, because solving this problem, from my perspective, amounts to, do you know these definitions? Because then if you don't, if you're in that confined time length of an undergraduate midterm, say 60, 90 minutes, however long, then that's how you separate out the wheat from the chaff. And this is the chaff talking here. So I sat down and I have 3 or so pages of, okay, well, 1 page doesn't count because it's just definitions, but then 2 pages of work. And then I feel like I had the solution outline in mind at this time. So that was the end of the day then. So I go to the next day and then I sit down, and my idea was, I'm going to screen record using my little computer tablet here, writing out the solution of the problem and recording that like this. And so I did that, I recorded it. I was a little bit interrupted in the middle because right now my driver's side front door handle on the outside is broken on my car. So I can only open my main driver's side car door if I go in through another door and like open it up or crawl over or whatever. So it's Thanksgiving break and I'm using this time to take it to the shop and go back and forth, and they order the parts and so on. So I had to take it to the shop for one of those going back and forths while I'm trying to film, you know, doing the whole tablet version of this video. So needless to say, I had like an hour and a half of raw footage explaining my solution to this problem. And in the course of doing that, I ended up having more details that I decided to work out more precisely, because I don't want to make an ass of myself in these videos for you guys. You know what I mean? I want to earn your guys' respect, obviously, for being able to do these math problems. You know what I mean? So did all that, stopped, and then I said, you know what? I'm going to do this the right way. And so I typed up in LaTeX the solution, and I think that's the best way of going about it, because when it comes to math like this, it's really about how clear and organized your thoughts are and how well you can convey that to other people who perhaps might not be day in, day out, having their hands dirty up to their elbows with this stuff that you're working on. You need to be able to convey it to the outside world, to real people, as you might say. So here we have it, the typed out exact statement of the problem. And so I'm just going to get into it. I'm going to go over the outline and the strategy first, and then I'm going to flesh out some of these definitions. Sorry, this has been a long rant in the beginning. I realize that, you know, some of the people who are watching these videos, you know, don't even have a math background. They might have a physics background. So I'm going to try to even appeal to those parts of the audience when I'm going over these definitions. So if you're like, why are you going over the definition of a group? That's why. So the outline is, I'm going to define a function. We're going to call it phi, lowercase phi, which maps the group capital G onto G mod H cross G mod K. Oh, damn, and there's no H there? I gotta fix this. I'm gonna make a quick note right now. The way I am making the LaTeX tech document is the text editor is Vim in a terminal, and then I just directly compile and then look at the PDF. Anywho, so I'm defining this function phi from the group G to G mod H cross G mod K, and then we're going to show that this function phi is an isomorphism, because for two groups to be isomorphic, then you have to show that there exists a function which is an isomorphism, which satisfies the properties of an isomorphism. And once you've done that, then you can say that these groups are isomorphic to each other. So how are we going to do that? Showing that a function is an isomorphism in itself has two parts. The first part will be showing that phi is a homomorphism, which spelled out means if you input x operation y into this function phi, then you get out phi on x operation phi on y. The second part of showing that phi is an isomorphism is showing that this function is a bijection, and this step in itself has two parts. And the definition of a bijection function is ubiquitous throughout mathematics. It involves being both injective, which is another way of saying that it's one-to-one, and the function is also surjective, which is another way of saying that it is onto. And we'll get into that in detail in a little bit here. Like I said, here are some definitions for the specific context to really get deeper into the problem. For those of you who are uninitiated, you may say, a group is an ordered pair technically between capital G and this dot, which we're calling an operation. And an operation could be either addition or multiplication, and often you'll see the operation symbol omitted. And in this case, capital G is a set. This could be a set of, say, integers, real numbers, Rubik's Cube permutations, but we have this set and an operation. This is different than, say, like the real numbers, which is not only a set and an operation, but there's a second operation, and we have a lot more properties to fulfill. For a group, we only have three. So just to put it plainly, parentheses work as we would expect them to. That's called associativity. And then we have what's called the identity element within that set. So whenever you have just a generic element and you apply the operation with this identity element, you get out that original generic element at the end. So whatever that identity element is, so if you have addition for integers, let's say, then that identity element is 0. If it's multiplication for the operation, then the identity element is 1, okay? And then the third property for a group is that we have inverses with respect to this operation for all of the elements of your set capital G. So if you have your generic element lowercase g, then G inverse is also in the set. So for addition, if you have a generic element of 1, then you would also have -1 in the set in order for it to be a group. If it were multiplication and your element were 2, then you would expect to find 1/2 in the set G in order for G to be a group under multiplication if you found 2 as an element in that group, say. So in math, whenever you have terms where you slap a prefix sub onto it, you can usually expect that it's where you have a subset of whatever the original parent object is, but that subset still obeys all the same axiomatic properties of the parent object. So, I mean, that's pretty close for a subgroup, but it's important to have, like I said, these exact definitions in mind when you go about doing problems. So this is, like I said, from the Dumb It and Foot Abstract Algebra book. The definition of a subgroup is the subset H of G is a subgroup of G if H is non-empty and H is closed under products and inverses. So if we have generic elements x and y in this subset, then we would expect to find x inverse and then xy, x operation y, in that subset in order for that subset to be considered a subgroup. Furthermore, this is kind of like a little proposition lemma, a little follow-up from that. It's not part of the technical definition, you could say, of a subgroup, but it's going to be important for the solution here coming up. The subgroup criterion. A subset H of a group G is a subgroup if and only if first H is non-empty, which is part of the definition, and for all X and Y generic elements of the subgroup or subset in mind H, then if H is indeed a subgroup, then we will find X, Y inverse in H. So it's, as you can tell, it's slightly different from the exact definition of a subgroup. But if this subgroup criterion is fulfilled by this subset H in whatever problem we're working on, then if we find XY inverse, then we know we've got a subgroup. Okay, moving on. What is a normal subgroup? So it's just saying that if we've fulfilled everything I've just said so far, then it's all of the generic elements, lowercase g, from our original group, capital G, which satisfied everything I just said. Then we have a subset, a subgroup. We're going to call it capital N, but we're going to look at only where it satisfies that. If we have this element, we apply it to, so we have generic element G. Let's call generic elements from the subgroup capital N. We'll call the generic elements lowercase n. But we have the set of all of these lowercase n. We take some generic G, N, and then we do G inverse. We still get out after that only elements in that subgroup capital N. So we only get those lowercase n. We don't get anything else that is in capital G, the group, when we do that. Okay, that's the definition of this normal subgroup. You could call the lowercase g n G inverse operation conjugation by the element G. So that is to say, these generic elements G, it's all of those that normalize N. Okay, that's how you sort of define what a normal subgroup is. All right, we're at 20 minutes, we got it. All right, and then I kind of already alluded to what an isomorphism is, what it means for two groups to be isomorphic to each other. So a group G is isomorphic to a group H if and only there exists a function, we're going to say lowercase phi, which maps G to H and that satisfies the following properties. First, phi is a homomorphism, namely if we input xy into phi, that's the same as doing phi of x and then phi of y. Furthermore, phi is a bijection, so it's 1-to-1. Phi of x being equal to phi of y implies that x is equal to y. And secondly, in order to show bijection, or the bijectivity, I guess you can say, of this isomorphism from G to H, we have to show that it is onto. So we have to show that it maps G onto G mod H cross G mod K, which amounts to showing that for all elements that are in the codomain, specifically, or for example here, I'm saying that this codomain is H, but in our specific problem, we're really mapping to G mod H cross G mod K. And so we're showing that G is onto that, which is maybe confusing because the order in some sense of G is 1, and then when you do a Cartesian product, it's an order of 2 in a way because there's those. Anyways, I'm not going to get into that, but for all elements in that codomain of our function that we're trying to show is an isomorphism, then that implies that there's an element in the domain, we can call it x here, such that phi of x will result in those elements of the codomain. So This is a part where a lot of you might have been looking forward to this. What does G mod H cross G mod K even mean? So we're just going to break this down piece by piece. What does G mod H even mean in the first place? Well, let's consider something that we can work with more concretely, and that's the integers mod n. And you denote this here. We have the z double bar / n z double bar. This can go one of two ways, right? You could have the operation being addition or multiplication. In this little toy problem, I'm first going to go with addition. Okay, you can say stuff like 5 mod 3 equals 2, or 5 mod 2 equals 1. So maybe you can hopefully piece together that 5 you could write as being 3 plus 2. So under the operation of addition, you have a remainder of 2 if you say that the base is 3, right? So 5 mod 3 equals 2 is a way of saying that 5, the integer 5, is equivalent to the integer 2. And if you have the integers mod 3, that set would only contain 0, 1, and 2. But obviously in the integers, we've got -1, -2, all the way negative infinity. We've got 0, we've got 1, 2, all the way up to infinity. But we can map the entirety of all those integers onto the set 0, 1, 2. We would call that the integers mod 3. We can change it up, say 5 mod 2 equals 1, but all of the same sort of lingo falls out. 5 is equivalent to 1 under the integers mod 2, where the operation is addition. And you could spell this out in exact set theoretic terminology. You would have A over bar is equal to A plus K n, where K is a member of the integers. And for these groups that we're defining here, n is fixed. So when we're looking at 5 mod 3 equals 2, we're fixing n to be 3, and we're saying, okay, A over bar is 2. This is a member of the integers mod 3, and it's equivalent to all these different A values that we can input from Z. They all map onto this same element 2. And you could do this whole example all over again. Instead of with the operation of addition, you do it with the operation of multiplication. And it makes it easier notation-wise, because then you could just throw away the multiplication symbol. So for G mod H, capital G, capital H, where the subgroup, capital H specifically, we could denote this all as the set of lowercase g times h to the n power, which that could also denote doing n times h if instead the operation were addition, right? Because you could say that nh is the same as doing h plus h just n times, but then if you switch the operation to multiplication, h to the n, we're combining the element h over and over with itself again n times, but the operation is multiplication. That's all this is saying here. And then we obviously denote, our lowercase g is an element of our parent group capital G, lowercase h is a member of our subgroup capital H, and n is an integer. You could spell this all out for G mod K. And this times cross, it's Cartesian product. So we define or notate or denote G mod H cross G mod K as the set of all elements x, y. We have this pair such that x is in G mod H and y is in G mod K. So yes, there are questions of commutativity which come in here. We could define this as h to the n and then times g, okay? And that, I think, starts to lend itself to why the problem is defined with normal subgroups. I'll talk about that more right now. So How are we going to define lowercase phi? If you have a normal subgroup, capital N, then you have that Gn G inverse is equal, or maybe equivalent is a better way of saying than equals, because if you have like a specific element of capital N and you do conjugation by G, so you do G lowercase n G inverse, you might not get out that same original lowercase n that you had on the input. But like I said, if it's a normal subgroup, then when you have all of the cumulative members of capital N as your inputs, your outputs are only going to be in that. So anyways, if you do a right operation onto this conjugation that's defining normal subgroups, you do a right operation of our generic element lowercase g, then this kind of gives you this loose commutativity. Because like I said, this doesn't mean that the operation on specific elements of your normal subgroup are going to be commutative. You don't get that guarantee. But you do get this equivalence that when you do a left operation of these elements of the parent group which normalize your normal subgroup, that's equivalent to doing the operation on the right, okay? So that's how we're defining lowercase phi here as GH and GK, and we're not losing anything by saying HG and GK and have to work out the details of all the subcases, right? Anyways, so now we're going to show that this lowercase phi function that we've just laboriously defined satisfies the definition of an isomorphism, the two parts, homomorphism, bijection. Bijection has two parts, injectivity, surjectivity. So homomorphism, you just crank through the definition. So for generic elements G1 and G2 in the group capital G, then phi of G1, G2 spelled out is G1, G2 capital H and G1, G2 capital K. So now we're going to just consider, what if we had done phi of G1 and then phi of G2? And so that's, now we're working through the specifics of that notation. So we consider G1 capital H and then dot or operation G2 capital H. This is kind of if the details of how Cartesian products don't work out in the way that I'm kind of assuming here, then perhaps things would fall apart here. If that operation dot in this line here, if that doesn't work out the way I'm assuming it does here, then I guess this would all fall apart. So, but if it does work out the way I'm assuming it does, then that is referring to the set of G1 lowercase h1, G2 lowercase h2, where these lowercase h1, lowercase h2 are members of capital H, the subgroup. So now if you just look at then the last three elements of the members of this set that we're considering here, by the fact that H1 originally was introduced when we were considering applying the function phi to the element G1, but that H1 is still a member of the subgroup capital H, so it implies that for H1, G2, H2, this is equivalent to saying there's some H1 over bar element within our subgroup capital H, so that we can write G2 H1 over bar H2, and this is the same as H1 G2 H2. And then you could just rewrite by, again, this H1 over bar and H2 being members of the subgroup H, we can just write G2 H prime. And this H prime is still in the subgroup capital H. So when we've spelled out G1H, G2H, this is all equivalent then to the set of all elements such that if we have G1, G2, H prime, and H prime is this contrived, you could say, H1 over bar H2, which is all still, regardless, not regardless of how we contrived it, but as we've contrived it, it is still a member of the subgroup H. So we've basically just shown that the first entry of our function that we've defined phi will hold up to this homomorphism property. So you could just show this all again for the subgroup K in the exact same way, and thus in total we have shown that phi is a homomorphism. So now the second part, which is a two-part demonstration here, we're going to show that our function phi is a bijection, starting with showing that phi is injective or one-to-one. And this is where the statement of the problem is important, otherwise the details may fall apart. As stated by Diego Torres in the comment, H and K are disjoint sets. I suppose if you were really strict about that, then that would imply that the intersection of H and K as sets, not necessarily as groups, but that the intersection of H and K as sets would be empty. It's the null set. But then H and K could not both be subgroups of G because only one could contain the identity element, say, or if one contained X, then the inverse could not be contained in the other one. So H couldn't contain X and K contains X inverse and then both be subgroups, right? So I take it to mean that the statement of the problem implies that H and K are disjoint subgroups, so the intersection of H and K as sets is only the identity element. I'm just going to denote this, though, the disjoint subgroups as saying H intersection of K. We're just going to agree that this is referring to intersection of groups and that that's E, that's the trivial intersection. So we're going to consider then, this is why I brought up the subgroup criterion, we're going to consider phi of G1, G2 inverse. Okay, so since we just showed that phi is a homomorphism, then when we consider phi of G1, G2 inverse, then that implies that phi of G1, G2 inverse is equal to, or is the same as, phi of G1 then times, or operation onto, phi inverse of G2. And we're just going to consider when this would possibly work out to be the identity element in the codomain of phi, because this is a construction, right? If we look at this and we expect that this is going to fail, this is not going to work out, then we're going to have a contradiction and, G1 and G2 are not, in fact, the same element, and it's just all going to fall apart. But eventually where this is going to lead is we're going to see that G1 and G2, as we've constructed here, actually are the same element. And so we're going to continue on here. It's just an explanation of why we're considering this, okay? So the statement that H and K are disjoint subgroups, as I just previously discussed, implies that the identity element in the codomain of phi, we're just calling it H to be reductive here. I'm not going to spell out or put in the subscript of this E here, frickin' G mod H cross G mod K. Okay, just hopefully just bear with me on the notation here. The way to get that element in the codomain of your function is if you input the identity element from the domain, say E sub G. You put that into phi. But in order for this all to work out, then the identity element in the codomain has to be the same as the identity element in the domain. Therefore, phi of G1 operation phi inverse of G2 must imply that that identity element is equal to what was input into those 5 functions, but at the beginning of the homomorphism statement a few lines ago. Identity element is equal to G1, G2 inverse, which then implies you could just do a right multiplication of G2, you get G1 is equivalent to G2. So we have thus shown that phi is injective, or it is one-to-one. To wrap this all up, we're going to now show that phi is surjective, or that it is onto, and this is where we are basically saved by the statement of the problem. And what I mean by that is that phi as defined does not necessarily guarantee, we're not really given enough information that for all possible generic element lowercase g operation onto the entirety of the normal subgroup capital H, and doing likewise in this Cartesian product with the normal subgroup capital K, we're not guaranteed for all of the possible generic lowercase g elements of whatever capital G parent subgroup we're working with. We're not guaranteed that there is going to exist for all of those GH, GK pairs, that there's necessarily going to exist a generic element, lowercase g, such that we can put it into our function and we're going to get all of the GH, GK pairs that we want. But we're saved, like I said, by the statement of the problem. However, the problem statement only requires that the group G be isomorphic to some subgroup of G mod H cross G mod K. So we're going to restrict our function to only those which result in the subgroup of G mod H cross G mod K. So yeah, I could definitely see why this would be a problem for an undergraduate abstract algebra midterm. You know, separating the wheat from the chaff. This is the chaff talking, but I hope some of you wheaties out there enjoyed this, and it's a little switcheroo from the normal differential geometry. Hope you guys like this. Maybe I'll do more like this. Drop a comment below with the problem. Maybe I'll make a video working it out. But until then, I will see you guys in the next one.